Hello all, we are going to solve a problem on stub matching. The load is given in this problem as ZL is equal to 450 minus J600 and the characteristic impedance are not as 300 ohms. The frequency of operation is given as 10 megahertz. Let's look into the theory first and then we can solve this with the help of Smith chart. Let's see how to proceed with the problem. Step 1. You have to find out the normalized impedance. How to calculate the normalized impedance? We have seen in the previous video. The normalized impedance is denoted as ZL bar, which is given by ZL divided by R naught. So for this problem, 450 minus J600 divided by 300. So ZL bar is equal to 1.5 minus J2. We are going to connect the stub in parallel to that of our transmission line. The line which is shown in blue color is supposed to be of the stub which is connected across the transmission line. So since the stub is connected in parallel with that of the transmission line, it is convenient for us to denote the load in terms of admittance, which is YL bar. So step 2 would be to find the admittance, that is YL bar. I'll tell you the procedure later how to find out YL bar with the help of Smith chart. Before that, what happens when we represent the load in terms of YL? As you all know, admittance consists of a conductance part and also a susceptance part, right? So the conductance part, I'll mark it here, YL bar is equal to a conductance part and a susceptance part. As you move along the transmission line towards the generator, there is a point where your conductance will be equal to 1 and you will have a new susceptance which is denoted as JB dash. To match the impedance of load to that of the transmission line, that is ZL must be equal to R naught, which means that ZL bar, which is equal to ZL divided by R naught, should be 1. This tells us YL bar should also be equal to 1. So this condition, if we attain this condition, that means our impedances are matched successfully. So that is what we are going to do. So when we move towards the generator, the first step is the location of the stub is positioned in such a way that the conductance part is becoming 1. And we do have susceptance, and this susceptance is being cancelled by the stub which we are going to connect. So the stub's susceptance is going to be minus JB dash. Okay. As a net result, when you add these admittances, you will get YL bar, which is your new value, is supposed to be 1. Okay, so we can achieve stub matching here or impedance matching here by converting our load impedance to a new value. What about this position? In this position, there is no matching is done. So there will be obviously standing waves till your stub, but after this position, we won't feel any standing wave because the stub has been placed in a correct position and you will have only incident wave. There won't be any reflected wave after this point. So that is the advantage. Here we have to find out two parameters, one being the position or location of the stub. So this distance, as I'm marking in yellow color, will tell me how much length, at what length we should position the stub. And one more thing, the length of the stub. I'll denote the length of the stub or I'll denote position of the stub as S, small s, and length of the stub as L. This L should provide a reactance or susceptance of minus JB dash so that our admittance will become 1. Now we'll see how to solve this with the help of Smith chart. We are going to plot the load impedance first, which is 1.5 minus J2. Okay, so we'll see first how to plot the value, that is the load impedance. I'll just mark the load impedance right here. ZL bar is equal to 1.5 minus J2. We'll see how to plot this on the Smith chart. As you can see, the real part should always be seen on the horizontal line. So the horizontal line, I'll just highlight the line. Here the readings are from 0.8, 0.9, and then this point is 1.2. This is 1.4 and the next point is 1.6. So 1.5 is right between 1.4 and 1.6. I'll highlight the circle. Since the load impedance is given negative, we have to go downwards because the reactance is negative. Okay, so the reactance should always be shown below. So this is 1.5 resistance circle. I'm just marking it right here. And to see the reactance, which is minus 2, we have to check right here. Okay, this is minus 2 circle, reactance circle, and the intersection of these 2 points is right here. Okay, this is the intersection. So here is where we can see ZL bar, which is equal to 1.5 minus G2. Now the next step would be to find out the admittance, which is YL bar. Okay, there is an easy way to find out the admittance with the help of Smith chart. All we have to do is first we have to draw the VSWR circle. How to draw the VSWR circle? We have to take the radius, the center from 1, okay, and the radius is ZL bar, right? Assuming this is your radius, you have to draw a circle and that circle will be considered as your VSWR circle. Right, so we have drawn the circle right here. As you can see, this is our load point, okay, and ZL bar, which is equal to 1.5 minus J2, okay, and we have to find out the admittance because in stub matching, as I told you earlier, this is your transmission line, okay, and it has some load, and we are going to connect this stub across the transmission line in parallel to the transmission line. Okay, so if we are going to find out the admittance, then that will be of very much helpful. Okay, so we have to find out what is YL bar. Finding out YL bar from Smith chart is very easy. I'll tell you the procedure. As you can see, this is your VSWR circle. Okay, that we have drawn just now, and it is drawn taking the midpoint as center and your load point as radius. Using the compass, we have drawn this circle, and from this circle, we have to extend the line that is joining the center and the load towards the opposite side. Okay, we have to join straight away, and this straight line will intersect your VSWR circle at a particular point. As you can see, it is intersecting right here. Okay, this point. So this point will be our YL bar, normalized load admittance. To find out what is the value of YL bar, we have to do the following. We have to track the real part in the resistance circle, okay, which is this circle. We have to track this. You should be very careful because you may follow the VSWR circle. You should not do that. To find out the real part, you have to track the resistance circle, and the value is 0.2 to 0.24. Okay, so the the conductance value is 0.24 plus J, and we have to follow the resistance circle, reactance circle, which is right here. Okay, as you can see, it is going right here, right? So this value is 0.32, that is our YL bar. Okay, so YL bar is given as 0.24 plus J 0.32. Now we have done this. Okay, we have find what is our load admittance. The next step is we have to move on the transmission line, okay, towards the generator, uh, at which point your load admittance should be transferred to conductance value as 1, and then you may get some susceptance value, okay, which is not sure, but then the conductance value should be equal to 1. So conductance value 1 means your resistance value should also be 1, right? So I'm going to highlight the resistance circle right here. This is your resistance circle, which is 1. Okay. So if your load admittance should be changed to 1, then obviously the point should fall on this conductance circle, right? And I'll also highlight in the downward direction. So this is our unity circle, right? Now we have to move on the transmission line towards generator, as I told you, in clockwise direction, that is towards generator. Okay, so this is our load. From load we are going to move towards generator. So towards generator is this direction. I'll just highlight it. Okay, this direction, and in this direction at some point you may intersect with your unit circle, which you have highlighted now, right? So the point is right here. Okay, this is your unit circle. So you have to find out what is the admittance right here. I'm just going to write down it here. YL bar is equal to, the conductance is being 1, and the reactance or susceptance, okay, the susceptance is 1.7, right? So plus J 1.7. Now this distance will give me the position of the stub, and I'm going to denote this distance as S. So how to find out the distance from this Smith chart? Okay, this is your load point, and from your load point you have to move towards generator, that is in clockwise direction, and in clockwise direction. Right. So I have drawn a line from the center and towards the intersection of your unit circle and the VSWR circle, and I have extended the line towards outside, right? So the position of the stub is the distance from this point to this point, okay, in this direction. That is our position of the stub. Now how to find out this distance? We have to take the readings which are increasing in this direction. So it is 0.0102 and it goes on. So if I'm going to observe the reading right here, it is 0.181 lambda. Okay, 0.181 lambda, because it is right before 0.182. So 0.181 lambda minus, if I'm going to subtract this point, which is 0.051, 0.051 lambda. So what I'm doing, I'm going to find out the entire length. Okay, entire length is right here to here, which is 0.181 lambda, and then I'm going to subtract this portion. So I'll get the remaining length, which we wanted. Okay, this is our required length. right? So 0.181 lambda minus 0.051 lambda. The answer is 0.13 lambda. 0.13 lambda. So this is our position of the stub. S is equal to 0.13 lambda. Okay, that is first point. And second point, now we have achieved the point right here. Okay, now the load point is shifted right here and the value is 1 plus J 1.7. As we have mentioned earlier, YL bar should be equal to 1. Only then the impedance will be matched. Okay. So what should we do? Here the YL bar is given as 1 plus J 1.7. So this 1.7 should be made 0. How we can make 0? If we are going to provide a negative reactance which is minus J 1.7, negative susceptance which is minus J 1.7, then when we add these two values we will get YL bar is equal to 1. Okay, so our stub should provide minus J 1.7 reactance. Okay, and the stub is short circuited. So I'll mark the short circuited point right here. This point represents short circuited point. Okay, and minus J 1.7 is right here. Okay, because the resistance part is 0, right? I'm marking the reactance on the outermost circle. That is real part is 0, right? Only we do have reactance part. That is why I'm marking it on the outside circle. Okay, so we are going to draw a line from the center. Uh, okay, we are going to draw a line from the center towards this reactance and I'm extending it outside. Okay, now since we are moving on the stub, just listen carefully. Before we used to travel on our main transmission line, that is why we were traveling towards the generator. Now a stub is placed across the transmission line, okay, and while traveling towards the load point on this transmission line. Okay, this is also a transmission line. Stub is also a transmission line. So when we move on this transmission line, we are going to meet a point where the transmission line is short circuited, which is this point. Okay, short circuited point. And we are moving towards load, not towards generator. Remember that for stub, we will be moving towards load. So towards load means we have to move in anti-clockwise direction. Okay, so anti-clockwise direction, which is this direction. Okay, so we have to find out the distance, the length of the stub that provides minus J 1.7 is this length. Okay, we have to find what is this length. So how to find out the length? We can take the reading that is increasing in this side. Okay, in this side, anti-clockwise. So here it is 0.01, 0.02 and it goes on, and this value is 0.25 lambda. Okay, I'll write it here. So 0.25 lambda minus length of the stub, 0.25 lambda minus, we have to subtract this length, right? Then we'll get the remaining length, which is what we wanted, right? So 0.162, 164 and 166. 0.166 lambda, that is the length. Okay, let me calculate it. 0.25 minus 0.166, okay, which is 0.084 lambda. That is the length of the stub, which will provide a reactance of minus J 1.7 that will be cancelled out when we consider the load point. Okay, so our load will be YL bar, which is equal to 1, so impedance will be matched. right? So we have measured two values as of now. The first value is the position of the stub. Position of the stub. We denoted this as S, okay, and the value of S is 0.13 lambda, and the second one is length of the stub, okay, length of the stub as we have measured 0.084 lambda. Now all the units, as you can observe, are in lambda. Okay, we have to convert lambda in terms of into meters, right? For that, in the problem, they have given an important information. Okay, what is the information they have given? They've given the frequency of operation as 10 megahertz. Okay, let me go back to the problem. So the frequency of operation is 10 megahertz, which means lambda is equal to C divided by F. C value is 3 into 10 power 8 divided by F is 10 megahertz, which is 10 into 10 power 6. So it is 30 meters, right? Lambda is 30 meters. So 1 lambda is equal to 30 meters. Therefore, the position of the stub, which is S, is equal to 0.13 into lambda, which is 30, right? So 0.13 into 30 will give me 3.9 meters, and length of the stub, which is 0.084 into 30, which is 2.52 meters. So the problem is over. We do have a transmission line, and we have marked the load ZL bar. From ZL bar, we have observed what is YL bar, and at a particular distance, we are going to positioning a stub, and the distance of the stub we are going to find out and denote it as S, that is 3.9 meters, and the length of the stub is going to be 2.52 meters. Okay, at this position YL bar will be equal to 1. Hence our impedance is matched. Okay, so that is how we have to find out the length of the stub and the position of the stub in single stub matching. Thank you.